So monitoring clock drift in Amazon EC2 environment, it was supposed to be a very short lightning node, basically based on like 3 graphs. But then I realized that maybe it needs some explanation as to why you actually may want to monitor clock drift or clock accuracy in your system. So why? In the case of the system I work on, we want to be able to answer a couple of questions about the data and the processes that happen in that system. A couple of example questions listed here is like, what customer data looked like at a given point of time? So time. What data was used by the customer to make some decisions in his business? This can be used, for example, to come up with good reports. What happened first? So ordering of events in the system, it may be important, especially in case of machine learning applications and so on. If you have a scenario where you want to establish, for example, what data the user might have seen that made him or her do something, then depending on the order of changes in that system, you may get some really wrong conclusions if your clocks or the order is off. You don't have to use clocks for ordering. You can use some other ways of accomplishing that, but normal time counting clocks are one option here. And last but not least, probably the most common application of clocks is to figure out when things happen. One of the applications here would be like monitoring, even at the infrastructure level, and correlation, very important for debugging in distributed systems, for example, when you want to figure out if 2 things might have caused each other. In the case of the system I work on, it's a fairly complicated setup. It's a service-oriented architecture, which is effectively a distributed database because each service has its own data store, communicates over the API. They don't share clocks, they don't share data stores. There's no consensus between the services and so on. So 70 different services, objects with relations spanning across services, multiple workers written in different technology stacks. What the hell?
I'm stressing you out, sorry.
No, you're not. And on top of that, everything runs on Amazon EC2, which implies VMs, probably different underlying hardware. This can lead to some problems as well, and Ubuntu Linux, which is not a problem. So what's actually the problem? I told you about a couple of use cases where you might want your clocks to be accurate, but what really is the problem that we are trying to solve that makes us really want to have very accurate clocks? If you think about a distributed system, like a service-oriented architecture, it's what you want in the end. If you want to build a data analytics stack on top of that, for example, and mainly, you want to build a system that behaves like an eventually consistent data store of sorts, even though it consists of separate pieces written in different technologies, not really sharing any storage and so on. But in the end, when you do data processing on it, when you get all this data in one place to run your MapReduce jobs, for example, you want to be able to reason about that data and be sure that the data is good, because in the end, if for example, if you depend on timestamps and timestamps are not good, then garbage in, garbage out, you're likely going to get bad results. In our case, what we want to do is to be able to build a data analytics stack on top of this already existing system composed of multiple services. And to accomplish that, we decided to kind of stream all the data, all the changes, all the facts into one single place, and then do analytics on that stream. But obviously, if you want to do meaningful analytics, you want to be able to tell when things happen in relation to each other. And obviously the clocks in that system are never going to be completely in sync. That's like physically impossible. So we need an upper bound on how much the clocks can be off each other, so that we can look into that data stream and say, okay, so I'm looking at some event A, and maybe there's another event that happened at the same time in another part of the system that's related to that event. How far forward in that stream or backwards in that stream do I have to look to make sure I can find the event if it actually happened? So we need an upper bound of sorts on the accuracy of our clocks. And then, of course, you can ask, are timestamps good enough? I mean, you can still have some changes that cannot be reconciled based on timestamps alone. But as a person doing the analytics, if you know something about the system, you can use this additional logic that you're aware of to remove, for example, invalid reordering of events. So imagine you have, I don't know, a user being created as one event, and I know some piece of text being submitted by that user to the system. Obviously, the only reasonable order here is for the user to be created first, and then for some piece of data being submitted on behalf of that user. So this is a very simple example, but we went through many scenarios, and it turns out to be feasible. So how do you build a system like that if you cannot do distributed transactions, because they are not very good for performance reasons, they are not very good for like liveliness of the system, and they are not easy to achieve either. You probably don't want to use like some single big data store for all the services to write into, because then for first thing first, you'd have to rewrite all the services to excuse me, to use this shared data store. And you know, maybe at Google scale, for example, you can have some huge file system that just scales massively, but like in our case, each service is really independent and they don't share data. And it's good for many reasons as well. So not being able to use some clever data stores, not really wanting to do massive rewrites that would, you know, be needed to implement stuff like vector clocks or whatever. We kind of assume that relying on clocks may be good enough for us if the clocks are not too far apart from each other. But how do we know? Well, NTP, the Network Time Protocol, it's a very good way of syncing clocks, and it can also be used to figure out how far a remote clock has drifted from the reference clock of sorts. So how well can we expect to do with this approach? I mean, if we want to actually rely on timestamps in our system and use NTP for time synchronization, so the usual evidence is that in a LAN environment, you can do something around 1 millisecond accuracy. If you get your time information from somewhere on the internet, perhaps 100 milliseconds with some errors is also good or doable. But in addition to that, we have to remember that we are on EC2 and VMs have problems of their own. So these are some quotes from like Stack Overflow or from some Amazon forums, for example, which evidence much bigger problems happening on these machines than you'd expect probably. 18 seconds drift in 5 days, I guess that's not really good enough. If you don't sync your clocks, that probably would make your data really bad quality at that point. The third quote at the bottom, someone is saying that they've seen clocks working at twice the normal speed. Not very good either. Some other pieces of evidence you can find on the internet say, for example, that if your VM is swapped out at the hypervisor level for like 10 seconds maybe, and then swapped back in, what you are going to see is like the clock jumping 10 seconds ahead, like instantly. We cannot really protect from this or against this with NTP, but something to be aware of, yeah. So without further ado, that was the reason why you might want to monitor the clocks. This is what we do, and the data is going to be based on our setup of 15 machines. We used to have more in production, but then we consolidated by a factor of 3, I think, so we basically replaced smaller machines with big ones. 15 is not a very big number for this kind of study, but I guess it's interesting enough, and as far as I remember, when we had around 40 machines there, the data looked pretty much the same. And so this is also going to be based on very traditional NTP setup, using the NTP pool servers of the ones available for Amazon. And what it gives us basically each host which is going to synchronize time with NTP gets 3 random, semi-random time servers from the internet. So this is something you may want to remember when you see the graphs, because you are going to see some variance in the times on these boxes, and this is probably caused by them obtaining their times from different time sources. I haven't tested the scenario where we'd start our own NTP servers in our data center and synchronize only from them, but this is something to be done maybe in the future. So the first set of data. This maybe requires a little bit of an explanation. The setup here is that we have our 15 boxes and one special timekeeper server. So what you see here is the time offset from the timekeeper, which just for the purpose of gathering this piece of data wasn't synchronizing its time over NTP. So it's basically drifting. And there's 15 lines there, one for each box, and they are all in sync using NTP. So what this shows you, one example, only one server. This is about 70 millisecond drift an hour, so over a month you'd be 1 hour late. Actually, is it late? No, it's actually speeding. So you'd be 1 hour ahead if you didn't monitor your clock drift and use NTP to correct that. This is basically the same graph, but now the timekeeper itself is syncing with NTP. So each line represents one host, and the value there is its offset in milliseconds from the timekeeper host. You might say it's pretty good, right? You have maybe 30 milliseconds from the slowest to the fastest clock, but as you can see, it's not very flat. Sometimes the clocks go faster, sometimes they go slower, and this graph actually doesn't look very much like stuff you see in IT very often. It seems kind of, like a physical process of sorts, which it actually probably is, because the clocks in the machines drift on their own, and there is the noise from the hypervisor also. So this is an interesting graph. What are these? Anyone wants to guess?
The hypervisor is mapping out the machine?
Might be. They correlate with these very well, and this is actually the response delay for the NTP query. This doesn't imply that the time on these servers was actually changed that much, but for that one query, something was off. You probably don't want to set up alerting based on this graph.
Did you put a histogram with this time? Like if this some standard distribution or something like that?
Do you mean the spikes or?
No, the previous one, the previous chart with next story.
One of the things that's really curious here, and I don't have an explanation for that yet. I asked around, but nothing so far. Why 30 milliseconds? Because it seems to be pretty constant at that level. I mean, there is some noise at the bottom here, which I could attribute to maybe small network delays. In Amazon environment, the round trip time is under 1 millisecond in terms of LAN. So why 30 milliseconds? I don't know. I haven't been able to find why do these 30 milliseconds? Because NTP, because it retransmits,
requesting the And time from NTP is implemented in C, C++, this kind of level?
For this test, it's in Python.
Because 30 seconds is...
No, it's milliseconds.
It can be precision of the counters of how fast you can get time from
No,
your
but it's not the
local.
case because you can see the noise floor here, and it's not 0 and 30 milliseconds. No, it's much better than that. But yeah, I don't know yet. So this is the aggregate of the previous graph of sorts. So this is the actually moving average on the range of between the smallest or the fastest and the slowest clock in our group. And as you can see, it's not very bad. Actually, we've been able to maintain about 20 milliseconds difference between the clocks or among the clocks. The moving average is there to smooth the spikes basically, and we actually have alerting set up based on this metric. The spikes weren't very helpful there. If we look at the data we have right now, so I used screenshots for the presentation, but here is like real-time data. We actually dropped to about 10 milliseconds spread right now, and it seems to be rising again. It looks like this at this moment. What happened here, I don't know yet, but it looks like the timekeeper host actually, I don't know, had a bad moment because all the clocks universally jumped in relation to that timekeeper host. So it's not something that happened on the boxes being monitored, but probably on the monitoring box itself. Yep. Do I have anything more? No. So probably too much explanation at the beginning, but the graphs were essential. I guess we could do better than this. My guess is that the spread here is probably at least partially because we use different servers from the internet and not our own setup of maybe 3 nodes that are very close to the machines, getting time from them. So for our system, which is at least right now mostly like human driven, we assume that even before we did this exercise, we assume that maybe if we can keep our clocks within 1 second, we are maybe good enough in terms of recognizing which action happened before or after another action, just based on timestamps, and it looks like we are well within this limit. So, but if you forget about NTP, or maybe you don't monitor NTP, it happens that the NTP server crashes, for example, for some reason. There are some internal checks inside the off-the-shelf NTP daemon that make it abort when it detects something wrong, for example, with its time servers. And we've seen one of the servers, for example, suddenly shoot into the sky when the NTP daemon dies and it stops syncing with the rest. Yeah, that's all for me. Thank you. Any questions? Yeah.
I didn't get why it was synchronized in the first place.
Yeah.
Because by default, the NTP server is enabled in Ubuntu, I think.
It's not.
It's not? Okay, so is it the fault of virtual machines or
it absolutely exists on
physical
virtual machines
as well?
You can probably do an exercise on your own local home PC. Just make sure you don't have some NTP running there. And I think like the cheap clocks you have in your PC may be drifting probably a couple of milliseconds a day at least.
Okay.
So there's the physical drift of cheap clocks. There's the hypervisor, which probably prevents the VM from getting accurate time or maybe timekeeping it accurately. And yeah, I don't know what else there might be.
So
But
actually the internal clocks in computers aren't that bad? Like it's like 10 seconds per day?
Yeah. Have you ever read the Spanner paper from Google? They have a very good study there of accuracy of clocks and how bad they can sometimes get in hardware at their scale, where they get thousands and thousands of machines. So Spanner, I think, actually relies on finding an upper bound or guaranteeing an upper bound on how much the clocks can deviate, and then they can actually do what, correct me if I'm wrong, but I think they do like transactions, distributed transactions without any locking, just based on like worst case scenario using current clock drift statistics or the upper bound they actually assume there's going to be. And they do crazy stuff. They have like GPS, master clocks and atomic clocks in the data center and some sophisticated setups to keep it all in sync. So yeah. If not now, catch me later. Thank you.